So plan for this week is let's start with chapter 3, getting into chapter 3 and doing some work. And actually this is a great review for what you're studying for chapter 2 on limits, rates of change, instantaneous rate of change. This kind of brings in what were a main point in calculus, the derivative. So let's just kind of recall really quick. At the beginning of the course, we looked at average rate of change versus instantaneous rate of change. And so I have here two functions. Let's look at the average rate of change. And so if we were looking at the average rate of change and maybe they gave us some value A, and then this would be, that was x equals A here, this y value we get back is f of A, and maybe this value here is B. And so if we go up here, this right here is our y value, so we can label that as f of B. So the average rate of change was the slope between those 2 points. Let's see if I can do this. And so the slope between those 2 points was the average rate of change. We also called this line that joined these 2 points that has a slope of between those 2 points, the secant line. So recall, this was called the secant line. But maybe we want the slope at one particular value. And so this is where we used limits, the concept of limits, to get the slope at one particular value. So for instance, let's say we wanted the slope right at x equals A. And so what we had done was we chose some value close to x equals A. And we always tended to choose it on the right-hand side of A, but we could have chosen it over here on the left-hand side of A. But we're trying to get some value or point close to x equals A. And so we said, okay, let's label that distance of the point between x equals A and this new point that we're choosing. And maybe let's say that distance in between these 2 points, let's give it a length of h. And let's take this and find the point right there when x, in this case, would be a plus h. So this right here is a plus h. And so if I went over here to find my y value, that would be plugging in a plus h wherever I saw an x in my function. This right here is my f of a value. And we wanted to find the slope between those 2 points. But that doesn't give me the exact value of what the rate of change is at x equals a. And so we said, okay, well, let's even get that value, that point, even closer to x equals a by shortening that distance of h, making that distance of h go to 0, or making that distance of h get infinitesimally small. And so that's where we came up with the concept of limits. And we said, okay, we're going to let this limit, we're going to take this value of h and we're going to shrink it. We're going to make it go to 0. So those points are basically laying on top of each other. And we're going to look at the slope between those 2 points. And so we said, okay, we're going to say, well, when we're looking at the slope between 2 points, we're looking at the change in our y value. So I'm looking at this f of a plus h, that y value for this point, minus the y value of the point where I'm trying to find the instantaneous rate of change. all over the change in our x. And so our change in our x, well, started with this point for my y value, so I have to start this point for my x value in the denominator. So a plus h minus this x value, which was a. Notice that in here, nothing simplifies in our numerator. That's a function evaluated at some x value, a plus h minus the y value in x is a all over. But our denominator, notice we have two terms or like terms, and a minus a cancels and we're just left with h. So we said this was called the instantaneous rate of change. At x equals a. And so when we looked at that, we found the slope exactly at x equals a, and we drew a line that went through our point and had the exact same slope at x equals a. This was called the tangent line. So this is our tangent line. Well, this instantaneous rate of change at x equals a, another word for that is we're taking the derivative of our function when x equals a. So derivative and instantaneous rate of change at a particular value, those are the exact same thing, just called something different. So let me give you the definition, and then let me also give you some notation on how we can write this derivative. So definition for the derivative of a function at some value x equals a. So the derivative of a function f of x with respect to the variable x is the function Okay, so this is our notation. I'm going to write the f here, and then I'm going to put this dash, kind of like an exponent there. So whose function, and I'll tell you in a second, is saying the derivative of f, whose value is the following. So this is just mathematical notation. So we have this f, we have this prime here of x. This is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. We have to say provided the limit exists. Okay, so that is some notation. So if we're talking about the derivative of our function, the derivative of the function is also a function itself. This is giving me basically the slope, any particular value on our graph, f of x. Let's look at an example really quickly. So let's say we're given a graph And looking at this graph, we want to answer the following question. So we want to estimate the slope of the tangent line. It says to each of the curve, or am I doing one example? So look at the slope of the tangent line of the curve at x equals 5. And we also want to find the equation of that tangent line. Okay, so it actually gives us a picture of what the tangent line looks like. So if you can see that, that's a red line. And we want to find the slope at this particular value here. And so looking at the tangent line, we know that the slope of that tangent line is the same as the slope at this particular value. And so looking at this, we can find the slope of a line by given 2 points. So we have a point, 1 point on the line that we're looking at 5, 3. And we want to find some other point on this graph. And so I would probably choose one that looks like a whole number. And so I notice here when x is 6, my y value is 5. And so my slope is going to be change in my y value. So 5 minus 3 all over the change in my x value, 6 minus 5. So looking at this, I get back 5 minus 3 is 2 all over 6 minus 5, which is 1. So this slope is 2. So looking at this, I know that the slope of my tangent line at the curve x equals 5 is 2. But another way I could write this, if this is f of x, mathematically I can write this f prime, the derivative when x is 5 is equal to 2. And then it wanted me to find the equation of the tangent line. So it wants to know what is this equation of the red line in here. And so in order to find the equation of the line, recall we need 2 things. And if we don't have those 2 things, we usually have enough information to find those 2 things. We need a point and we need a slope. Well, I have my point, and that is 5, 3. And I have to use this point right here where we're trying to find the equation of the tangent line. I would not use this point up here. So we have a point at 5, 3, and we have the slope we found was 2. So a couple ways that you can find that equation of a line. You can use your point slope formula, y minus y sub 1 equals your slope, m times the quantity x minus x sub 1, or I tend to like y equals mx plus b. We know what y is and x is for one value, and we know what our slope is. We could figure out what our y-intercept has to be on that line, and then we would have the equation. And so if I go in here, I know y is 3. This has to equal my slope. My slope here is 2 times my x value. And my x value is 5 plus b. And so I have enough information here to figure out what my y-intercept is. So 3 is equal to 5 times 2, which is 10 plus b. Get b by itself, I can subtract 10 on both sides. So I get b is 3 minus 10, or negative 7. I'm not done. I want the equation of the line. And so I need to go back in here and I need to plug in what my slope is, which is 2. So I get y is equal to my slope 2 times x plus b. But my b value in my case is minus 7. So this would be minus 7. And so that's the equation of the tangent line when x is 5. Okay. Okay, so again, kind of good review of what we had started with at the beginning of the course with average rate of change and instantaneous rate of change. And now we're just kind of calling it a little bit different. We're saying the derivative instead of the instantaneous rate of change at that value f(x).